Welcome to this video on calculating capacitance of a cylindrical capacitor. This is going to be part one of two because as I made a draft or two of this video, it gets kind of long because there's quite a lot to do here. But this is a great process. This process truly encapsulates everything that we've talked about so far in electrostatics, and it really puts all of the knowledge to use and application. But when you get a little disheartened or lost along the way, just remember the big picture here is that we're trying to figure out the capacitance for this coaxial cylindrical capacitor. And the capacitance is just the amount of charge stored on a plate based on the potential difference across the plates. Now, if you're thinking, well, where the heck is a plate? Because I don't see any plates here. If you think of these as toilet rolls, right? One big toilet roll, like just the cardboard part, and then the inner toilet roll. If I cut along the side and I flatten it out, I have two plates, right? I have an inner plate and an outer plate. But you may be thinking, well, one of the plates is small, and the outer plate is going to be big once I cut them and roll them out, right? And you're correct. And so the big thing here is that it's different than the electric field it's different than the electric field of the parallel plate capacitor, because that was a constant electric field and this is a non-constant electric field. That's why this is going to take us a little bit of time. Now, what I'm going to do is I'm going to outline my process, and this process is the same as what we did on the parallel plate capacitors, but now it's going to be obviously just a little bit different because I have a non-constant electric field. So I'm going to write my note here that the E field, or the electric field, is not constant. Now, the important thing about this process is, what electric field are we talking about? We're talking about the electric field that's in between these two plates. That's the part that's contributing or will store the energy of this particular capacitor. Now here I have a top view so we can look at it and write some things in a little bit more clearly. And if I draw the electric field in, I first need to tell you what some of the values are here. Let's say that the inner radius is radius A, outer radius is radius B. The inner plate is going to be positive Q, the outer plate we'll call negative Q. Now what we're going to do here in this case is we're going to use Gauss's law to figure out a bunch of things about the electric field. But we could draw, because we know the inside's positive and the outside's negative, we can draw the electric field lines in, do simple things that we already know how to do, away from positive towards negative, from high potential to low potential, and we see that the field lines are diverging from this point, and so that means that the field is not constant. Okay, and we can use Gauss's law to figure that out. Now, the reason that we have to do this in 2 to 3 parts here is because of this guy over here, voltage. Q is Q, right? Q is this. We could write other expressions for it like lambda L or sigma A or different things like that, but that's not really that big of a deal here. It's the voltage that's the real kicker that's going to make this take a little bit of time, because we know that voltage is equal to integral E dot dr. Okay, and I'm specifically not putting the negative sign here because I'm not talking about specific directions or anything like that right now. But if I look at this definition, I know that I have to find the electric field. I have to integrate that function with respect to R, okay? And then I can know the potential between the two plates. Obviously, this is implying that one of the plates is 0. And we'll call the outer plate 0. That's why I just have V here instead of V, 1 minus V2 or VB minus VA. I'm going to just leave this kind of generic for right now. So here are the steps. Step 1 will be to figure out the electric field. Step 2 will be to then integrate that function and figure out the voltage. And then step 3, of course, will be to do what we are actually trying to do and find the capacitance. But I don't want to shortcut anything. And although we talked about the electric field around a cylindrical or a line of charge before, we want to make sure that we truly understand what is happening in this situation. So what I'm going to do first is I'm going to try to figure out what the electric field is in 3 different regions. when R, right, this is the position that I'm picking specifically to describe the electric field, when R is less than A. So when you pick a point on the inside here of this inner core, what is the electric field? When E, the electric field, is at a point when R is greater than B. So out here on the outside of the capacitor. And then, of course, the most important one, the electric field when R falls between A and B. So this is the whole thought process involved here. And because we know that if we know the functions of E, then we can know what V is by integrating those. And so it's important for us to really understand what we're talking about so that we can make this process a little bit easier if we change something up. Okay. Now, the electric field between the two plates is the one across which the potential difference is that we care about. So it's really this one that matters most. But let's see if we can apply it to these other two. Like I said, I'm going to use Gauss's law here for step 1. And Gauss's law is, remember, the electric flux is going to be equal to E dot dA, which is equal to the amount of enclosed charge over epsilon naught. So I make Gaussian surfaces in these different regions, and I should be able to figure out the electric field. So let's do that. I'm going to go ahead and make a Gaussian surface on the inside here, inside the inner cylinder. Okay. Now, the Gaussian surface that I'm making is a cylinder, right? And so just so you remember that it's not like this, there's no enclosed charge. And the fact that there's no enclosed charge means that there's no electric field on the inside here. So I'm going to go ahead and actually just write this in here. The electric field when R is less than A is just 0 newtons per coulomb, or I'm going to put here volts per meter, just so we remember that's an option for the units. Now, you might be thinking, wait, you said the inner core was positive Q, so now you're saying that there's no enclosed charge? What the heck? Well, remember, this process employs all of your knowledge, and for a conductor, right, a conductor, the charge will distribute on the outer surface. So that inner cylinder, the outer surface contains the positive Q charge distributed throughout, not the inside, and so the electric field inside there is just 0. Now when I make my Gaussian surface on the outside, where R is greater than B, right, again, I have 0 enclosed charge because positive Q and negative Q cancel out and I have 0 enclosed charge. This means that 0 enclosed charge again, 0 newtons per coulomb or volts per meter, and so no electric field on the outside. It's this one that we actually have to do some sort of calculations for. So let's make the Gaussian surface again. Make our Gaussian surface at any point on the inside here, because then we can adjust the value of R. I'm going to call the radius of my Gaussian surface R, right? The radius of the inside one's A, the radius of the outside one's B. So my Gaussian surface, okay, the Gaussian toilet roll, if you will, right? The one that's in between the two over here and here, that's the one that we're talking about now. Okay, and it doesn't actually exist. We're just using that to figure out the flux. So what we're going to say there, that Gaussian surface where we have chosen it to be, the electric field is constant everywhere along that surface. So I can pull E out of the integral, and now I need to do something specific with Q enclosed, because I'm not enclosing the entire cylinder, right? I'm enclosing a portion of it so that I can help establish this. So instead of writing Q enclosed, I'm going to write lambda L, and this is the lambda L from my Gaussian surface, right? It's the Gaussian amount of enclosed lambda L, right? So it is technically the charge that I'm enclosing, but these are the dimensions L of my Gaussian surface, not of the entire thing, right? And that's over epsilon naught. Now if you think about it again, if I cut my Gaussian toilet roll, slit it along one side, and I lay it flat, I've got a rectangle essentially, right? Now if I draw in a dA vector for the Gaussian surface, and I know that my electric field that I already drew is pointing outwards like this, okay? I know that the cosine of the angle between these two vectors is 0, and so the dot product is going to be 1, and so that's great. I don't have to worry about that. The end caps of the Gaussian surface, so this part of the surface and the bottom piece of the surface, there's no flux there because dA, of course, and E are at 90 degrees to one another, and the cosine of 90 degrees for the dot product is just 0. So I'm only dealing with the sides. So when I integrate all the pieces, right, all the little pieces, I'm going to get E is equal to, E times 2 pi r of the Gaussian surface times L, which is the length of the Gaussian surface. So that's just the surface area of the sides of my Gaussian toilet roll. And then I'm going to have lambda L over epsilon naught, and I see that the L's cancel. Another really cool thing about this process, the L's should cancel, right? If you think about it, the Gaussian surface, the Gaussian toilet roll that you choose, the length of it, you could have picked anything arbitrary, right? And that should not influence the strength of the electric field at any point in here, right? So the fact that that cancels out is really a good thing. It makes it known that the Gaussian surface is a tool, it's not the actual thing. So I'm going to write here, I'm going to divide by 2 pi r on both sides. I'm going to say my electric field is equal to lambda over 2 pi epsilon naught times r. And this is the electric field between the two plates. Now, at this point, what I'm going to do is a quick little sketch of the graph here, because this is where we'll pick up in the next part when we actually try to integrate this function, and we're going to go from, we're going to do electric field as a function of r. I'm going to put a, so 0 to a, this is the inside, right, and then a to b. And I'm going to go ahead and put this in. Now I'll pick a thicker line so we can see it. I'm going to say, we said the electric field on the inside was just all 0. We said the electric field on the very outside is all 0. But the electric field here is a function 1 over r. So if I kind of draw this, it would be something that looks like this. Okay, and so we have this function. Now to set us up for the next video, conceptually, what we're trying to do here, okay, let's go back to our original thickness. Essentially what we're trying to do here is we're going to make a graph of V as a function of R. Here again, A and B are these specific boundaries. And if you think about it, the integral of all of this, right, if you integrate E with respect to R, we should get the functions for these different regions, V through R. Let's go ahead and just do these outer ones, right? We will say that if there's no electric field, there's no potential difference. There's no electric field, there's no potential difference. Now we have to figure out potential difference being 0 is not the same thing as potential being 0. So that's where we'll pick up in the next video.